In this episode, we are going to debug and inspect directly inside the ELF executable file which get generated after the compilation stage. The file named as hello world, which is green in color, after the compilation finishes we get that file, and we are saying that this is a structured binary format which kernel understood and run it directly. So what is inside that file that kernel understood it easily? So gcc hello world.c hyphen o hello world. This command generate the ELF file. So you will get one ELF file. Hello world. When you check this file type, this is ELF executable file, which is dynamically linked. I already explained in the previous episode that we have two type of linking, static and dynamic linking. Our ELF is dynamically linked, and the which is interpreter. This is the interpreter. This is the library, and this is the magic code and our operating system. Okay, so hello world is an ELF file. So ELF file is a structured binary format which can be easily understood by the Linux kernel. It combines the object files along with the libraries. Link the libraries, and we get the library shared libraries. We get the ELF. So ELF is like a blueprint, which is map for execution. We can say ELF is blueprint of execution. Now ELF header means all the necessary details. Header means some identity card type of. It has all the necessary details, like we can say what kind of architecture means, whether it is 64-bit or x86, or it is on ARM based, or x86 based 64-bit or 32-bit, whatever is the architecture, we get that information from our ELF header. Third information, entry point, which is a very important and crucial information. Entry point address. Entry point address, which is used by the kernel to enter, the kernel execution mode. And the offset to program header, from where memory should be read. So offset. Program header means we have second layer as the program header, and this is the offset layer. ELF header is like an identity card which gives the basic informations like our file type, architecture, magic number, entry point address, offset addresses. Otherwise, how I can check? So we have one Linux command to check it. Our ELF file is hello world. We need to inspect header file. So read ELF -h hello world. The command, okay. So here is all the information. Magic is unique to our ELF. Class is ELF 64. 64 is our architecture. Little Indian, version, type, machine, entry point. This is the entry point address, which is very important information. All the files. Start of the program header. Second part is program header, where it got start, section header. What is the size of this header? Size of program header, number of program headers, similarly size of our section headers, as well as number of section headers, and the section header string table index. So all this information we will get into our ELF header. So all the necessary information what is required for the kernel to enter, we get into the ELF header. Now our second section is, so most important thing you need to check is entry point. Entry point is entry point address. Whatever we can say, this is where execution began. So I will show you what is at that address inside our program header. Okay, so let's move to second section, that is our program header. Okay, after the ELF header we are moving to program header. This is like an execution map. First thing, just write command to check the program header. Read elf r e a d. Read elf. Okay. For the program header, we have -l and the elf file name, that is world in our case. Program header has information like what to load and where in the memory and with which permission, because permission can be read, write and executable. These three critical information is in the program header and it is very important information. Program header is used by the kernel. Okay. Command is read elf hyphen l and our elf file. This all information we have in elf file is DNN, position dependent executable file. Entry point address, this address we get from the header section. 13 header section starting at offset this. Now when you see the program header, we have these four informations. It is offset address, virtual memory address, physical address, file size, memory size, flags and alignment. Okay, and these these all are the permissions. I say na, every thing has the permission. So R is readable permission, physical address, interrupt, load. So requesting program interpreter. Interpreter is our library. Now that is can be seen by the library. This is segment 2, section 2, segment mapping information. RO, read-only data will be available in 4th section. These all information. Dynamic data will be available in .c section. So these all detailed information is available now by the kernel, so that kernel can read and understand, okay, I need to move to this particular address to find the information. So this is in our second layer. Third layer is section header. This third layer, and which is section header. First layer is like identity of an ELF. Second layer is used by the kernel. This third layer is actually used by the linker, or we can say debugger also. This is like an logical organization, like in the program header, which is an like execution map. This section is similar to our logical organization. Everything is logically organized into this section so that it can be easily understood. Important section from a programmer point of view. -s. S is for section. -x, ELF file. ELF file here is hello world. Section header, which is used by the linker and the debugger. Section header is basically a logical organization of ELF ELF data. The command to check the section header is read elf -s hello world.c, and we have in the section header we have different types of sections like .text, .data, .bss, .string, .ro, and there are multiple sections. In each section we have some different types of information available. Like in the dot section we have code part, which has a different permission, like code is usually read only permission. In the data section we have all the global variables, whatever we assign in the code goes into the data section. Similarly, in the bss section global variable only goes, but here all the uninitialized global variable goes. Dot string, whatever strings we are using in the code part, that goes into dot string. Like in our program we have used welcome to embedded internals, so that string part will go into dot string. Similarly, dot ro data, only read only data will go into this section. And similar to this we have multiple sections which everything that is under section header. They are used by the linker for grouping and very useful for the programmer, as we need to debug the code by using this information. Okay, I will show you what is inside this. Read elf -s and our elf file, that is so such a large information. So this dn symbol, dynamic symbol, contains 7 entries. Okay, now we will see the entries. This is index, function type, either this function, no type, anything. This is glibc, which library is called. Putc is for printf function, which is used in our for code. Global. This is our file hello world.c, which is type is file. This is local. Visibility is default. This. Some construction and deconstructor are being called. Clone is process calling. Now main is also a function. Main is a function which is being called by bss start, that is being called by is underscore start. So from the kernel perspective, we can see that underscore start is the first function which call the main function. Okay. We have a dedicated episode on what happens before main, so we will cover this, how underscore start being called from the kernel, that actually calls our main function as a callback function in detail. Before moving forward, I just want to clear one point, that sometimes we are using the word section and sometimes we are using the word segment. How the section and segment differ from each other? When I say section, I am referring to how the linker is using it. Section is at linker level, okay, whereas segments are at kernel level. Same information, but how the mapping is, that the purpose, like sometimes we are doing the logical grouping and sometimes we are doing the memory grouping. For the linker, we are doing the logical grouping. So like dot section, dot text, dot data, we know that all the global variable will go into the data segment. BSS will contain this information, stack will contain this information. So we have just logically grouped it. So logical grouping means section. When we say segment, it is memory grouping, how the kernel will see that into the it while loading memory. So when you see the statement like load, this is memory grouping. When you see statements like dot text, dot data, dot ro data, dot symbol, anything, that is a part of section and that is a part of linker. Linker see this information into, groups the information into this way. How to load that elf file into, how kernel loads elf file. So to load it, we give this command dot slash hello world dot hello world. So these 6 steps is being done by just by when you write one command kernel, these validation. First is to read elf header, then it validate the format, then it validate the program header, then it maps the segment into memory. After that is stack, set up the stack, and after setting up the stack or doing all the preprocess step, it moves to the entry point from where our execution begins. So you might be aware that how the memory mapping is being done. Okay, I will show you. This is a program. Let us run this program. Let us do some tweaks in the program and run it again. I am just adding a simple sleep call inside this, so that program will run for few milliseconds. In the meanwhile, we will validate our memory mapping. Okay, that's the reason I have included sleep. So after doing the modification, we will run the gcc.c-o hello world to get the elf file. Now the new elf file will be generated at this current time. Elf file dot slash, we are running this elf file hello world. Okay, in the process list we find that okay, this is the ELF file which has this process ID. So let's move to this process ID, cat prop 1178, and we need to check the memory mapping. So maps, okay, this is the memory mapping of our program which is seen by the kernel. So let me show you. This is our program, execution awareness, episode 4, hello world. This is our library. This is our heap segment which has a particular permission of read write. Okay, these all are the segment. Like heap segment, we have stack segment, and different memories has been allocated to different parts with different permission, vwhere, vdso. So this is and this area, this is the memory starting and the ending range. So our stack segment start from some 7ff this 5000 to this address. This is the address, segment address of stack segment. Similarly, we have address of the heap segment. Different segment got starting and the ending memory address. We have one dedicated episode on our memory segments where we will explain how the stack, heap, and all other segments will look into the memory, what kind of memory it get allocated, and how we are modifying the memory, and when we cross the segment what kind of errors we will get and how we have to debug that. Stay tuned. So one more thing I just want to explain. So this is the memory mapping. If you see, if our program is still running, okay, program execution finishes, so it's removed from our list process table. The thing we need to check is what kind of library is being used. We have seen the dynamically linked library. So let me show you from this. Let's validate that. For the dynamically linking library, we need some kind of library. And what is that? This is shared library. Shared library means it is dynamically linked via libc. Libc is our C program library, libc.so.ss. This is needed, means this is a necessary information without which our program will not move forward. We will not able to run this code. So to check the library information, we will use this command. These all information are very important when we are debugging a very crucial codes, because dynamically linking information is very important information. It gives the library whichever is being used by the program. So whatever is marked as needed means that is the information without which we will not able, kernel will not able to process this. We have checked all the header files of ELF, all different files. We have in-depth detail discussed on about every segments, every header, every part of ELF file. Now we are moving to check how to disassemble the ELF format. We have object dump. Just disassemble every part of our code. We have main function, we have the statements, we have sleep cycle. So everything is being disassembled into the assembly code in this area. So this is the assembly part. So hello world is in file format, this init section, init is start section. You need to have some understanding of assembly language to understand this. So push, jump, this is a particular address, IP address, AX, these are the CPU registers where these commands is being stored. This is our sleep function which we have called. This is our puts printf function which we have called. And these are being used from stdio header file. And these all are the part of main function. Okay. So when whenever you inspect any particular function, you will see where from where each system library call is being called. This will help in debugging. Summary of our today's episode, we have header, ELF header, which is like an identity card. All the detailed information is there, basic information. Then we have execution map, which is used by kernel. This is like segments, or we can also say program headers. Then we have logical data, which is being used by the linker, which we can also say section or section header. Then we have all the dynamic information. We have checked the libraries, dynamic info, or dependencies like libraries. Each section is being inspected by a particular command, like we can inspect header by using another color, by using read elf underscore h or whatever is the elf file name. Segments or program header can be inspected by using read elf hyphen l and the elf file form name. Similarly, section can be logical data or section can be inspected by using hyphen s and elf file name. Dynamic dependencies can be checked using LDD, or we can also check using read elf hyphen. Let me show you from this. So what's the command for checking the libraries is hyphen d. Okay, read elf hyphen d and elf. And to disassemble each elf file section, we can use object dump. This is a very important command. Object dump hyphen d, or you can use any function and elf file name. Okay, so this is quick summary of today's episode. In the next episode, I am going to cover program execution pipeline in details. Thank you.